So, okay, good day everyone, and welcome to the second talk of this series. That is, Buddha is giving on physics of distillation, distilling, secrecy, and entanglement. In first talk, Buddha already discussed the basic scenario, but now today he will discuss more elaborately starting from Shannon. So, Buddha, start.
Yeah. So, as Manik told, though this is a talk on physics of distilling, secrecy, and entanglement, but today's lecture almost doesn't involve physics. It is mainly information theory, and maybe it is very basic talk, and maybe for most of the people these are trivial talk, but I'm thinking that there are some students who have started reading this subject very recently. So for them, it may be good. But other important thing is that if this thing can be understood, then this quantum, physics of distilling, secrecy, and entanglement will be understood in a better way. So this is this is a very basic talk. And it's mainly involved Shannon theory, Shannon Bodhi theorem. Yeah, let me go. So Shannon comparisons theorem is a very, very powerful theorem. This problem can be posed in this way. Let I have a biased coin. That means with p probability head comes and with 1 minus p probability tail comes. And I toss the coin, say, 8 times. So how many possible sequence of results we can get? Possibilities 2 to the power 8. Now I have done it. I have caused the coin 8 times, where n is very big, and I want to convey this sequence to my friend. Then how many bits will be required? Now Shannon has shown that if n is very large, then though there are possibility of 2 to the power n number of sequences of head and tail, only those sequences where pn number heads are there and 1 minus p n numbers tails are there, they will be most probable sequences, and sequences which does not have this property, they will not almost appear if n is very large. So, and then Shannon calculated what is the number of sequences which has this property. That means the sequences of head tail which contains p into n number of heads and 1 minus p into n number of tails. And after using all these Starling approximation and all these things, he showed that number of typical sequences is 2 power n into hp, where hp is the Shannon information expressed by this quantity, this expression hp is equal to minus p log p minus 1 minus p log 1 minus p, where the base is 2. So Shannon's idea is that to convey this result, I mean the sequence of head tail to your friend, instead of using n bits, you can use n into hp bits, and that are necessary. And actually, he proved it to be necessary and sufficient. So, why this is called comparison? Because instead of using n bits to convey this information of head tail, you can convey this information with n into hp bits, where in general hp is strictly less than 1, less than equal to 1, but when p is not equal to half, then it is strictly less than 1. So indeed you have increased the necessary bits to convey this information. This is Shannon result. Is there any question on this part? If not, I will go to my second slide. So from now on, whenever we will collect a sequence from such source where something is there are two possibilities, maybe bits, maybe head or tail. If their probability is this p and 1 minus p, then the sequence that we will consider from now on, they are only typical sequences. We will not care about atypical sequences. Now, towards Shannon channel coding theorem, to understand Shannon's channel coding theorem, which we will also use for deriving secrecy. So again, I am defining in a more general way. Consider a random variable x whose value can be xi with probability pi. Then what is the Shannon entropy of this system? It is hx, which is nothing but minus the summation over minus pi log phi. And if you take two variables x, y, where they may be independent, they may be dependent, they may be x may be input, y may be output, but we are considering two variables xi and yi, and the probability of that probability of xi yj is pij. Then you can calculate this Shannon quantity of this joint distribution in this way. Same thing. Summation over ij minus pij log of pij. And conditional entropy, that means y given x, y given x, this is actually hxy, that means Shannon entropy of this joint probability minus Shannon quantity for y variable. This is something like this, that after knowing hy, how much ignorance remains for the variable x. That means knowing y, how much entropy remains for the variable x. You can think this in this way. And mutual information is this, I will use this symbol, hx minus hx given y. That means after knowing y, how much ignorance you can reduce for your variable x. And it is also symmetric, can be written in this way also. But whatever this thing, final expression is very simple. hx plus hy minus hxy. So this is Shannon mutual information, and this quantity, both these quantity are very important for this channel coding theorem and also for deriving secrecy. Now, let us develop the basic ideas. If we can understand this.
Hello.
Yes.
Hello. Yeah. I have a question. What is the difference between this conditional entropy and mutual information?
Conditional entropy means after knowing y, how much ignorance remains for x.
Okay.
So mutual information means knowing y, how much ignorance you can reduce for the variable.
Okay.
So it gives some kind of correlation or mutual information. If they are perfectly correlated, then this is equal to 1 for a bit. Yeah. Okay, it will be more clear as we proceed. Now let us discuss about developing the basic ideas, because if this can be understood, then Shannon's most general theorem could be understood easily. So, but we are taking very idealistic case. Let us start something like this. For every two use, there is a channel where x is input, y is output, but we are taking bit channel. That means through a single channel, you can send one bit. For every two use of the channel, I mean bit channel, one channel may act imperfectly. So for every two use of the channel property is such that one channel may act imperfectly. That means with some probability, it may act imperfectly, that means it flips the bit, and with rest of the probability, it does not change the bit. So sometimes it acts perfectly, sometimes it acts imperfectly. But one of them. Now, let us try to see whether a perfect bit can be sent by such use of two channels. So we will be using the channel twice. So what we do, we take this encoding. We encode 0 to 2 bits, 200 and two zeros and 1 to we encode 1 to 21. Now, so I am using the two channels to send either 00 or 11. If my information is 0, I will send 00. If my information is 1, I will try to send 11. But because of these properties of the channel, 00 will go to, it may remain perfect 00, or it may be 01, or it may be 10. So the these 3 0 0 0 1 1 0 that is contained in the red circle, these are the possibility of the output if the input is 0 0 because of this channel property. And if the information is 1 1, then the possibility is 0 1 1 0 and 1 1. So this blue circle contains the output. So you see that sometimes if your friend gets 0 0, he will understand that of course you wanted to send the information 0. And if your friend gets 1 1, he will understand that you wanted to send the information 1. But when 0 1 and 1 0 are the output, they will be confused. You will be confused because this 0 and 1 0 may come from both. So information cannot be sent reliably with such channel if you use the channel twice and if you encode in this way. And there cannot be any better encoding by which you can send the information reliably.
Guruda,
Yes.
can you see this? Can you see this problem in this way? There are
একটু জোরে বলো.
Can we see this in this way? That there are two bit channels. One is perfect, one is imperfect.
Yes.
But which one is perfect and which one is imperfect, we don't.
Yeah.
Now the question is, we have to send one bit of information. Is it possible to send reliably?
Yes.
The answer is it is not possible.
Yeah, it is not possible. At least reliably.
Reliably, yes, exactly.
Yeah. Because of this intersection.
Yes.
Between red circle and blue circle. So let us try something else. For every 3 users of the channel, one channel may act imperfectly, as we told, one of them. Which one we don't know, as Manik told. Can we send one bit of information perfectly by using 3 channels? Here the answer is yes. What you do, you encode 0 to 3 zeros and 1 to 3 1. Now, 3 zeros by using 3-bit channel, its output are in this red circle, which is this 4. And 1 1 1 will go to, output will be this circle, blue circle, where these 4s are possible output. Now there is no common sequence. So you can reliably transfer 1 bit of information for such channel. Property of the channel that if you use thrice, then one of the channel may be corrupt, may behave in a corrupt way, but which one you don't know, as Manik was trying to tell. I think things are clear. Here, reliable transfer of 1 bit is possible. Yeah. Now, but this is very idealistic type of case. In nature, actually, such thing don't happen. Nature, what happens? That you have to characterize the channel. So channel is something like this. Every channel, let every channel behaves in the same way. And character of the channel is something like this, that with P probability, it flips the bit and with 1 minus p probability, it does not change the bit. And every channel behaves in the similar way. Now the question is, if now you are given the freedom that you can use the channel any number of times, let's say n times, where n is very large. Now the question is, can you say, first question is, if the channel is corrupt in this way, is it possible to send your information perfectly? And Shannon is a very, very beautiful theorem. Shannon told that if the channel conveys something, that means conveys something means P is not equal to half for bit channel, then of course information can be sent perfectly. Maybe you have to use the channel many times. This is the essence of Shannon's channel coding theorem. That if the channel conveys something, it does not randomize the whole message. That means P is not equal to half. Then, of course, you can send your information perfectly, but maybe you have to use the channel many times. So
Sir,
yes.
I have a question here.
Yeah.
So in this study, I think this IID assumption has been taken care of, right?
Yeah.
Okay. So if I don't take IID assumption, I personally don't know about the IID assumptions that much. But if we don't consider IID assumption, still this result will hold.
IID means source. From the source
Yes.
it is coming. So
No, I think for the channel. I don't know.
Channel is behaving in the same way. Yeah, this is also assumed. Then of course, if first use of the channel somehow influences the second channel in its behavior, then things may change, of course.
Okay. I mean, I also don't know much about the IID assumptions, but
but then these analysis will not run.
Okay. Thank you.
For the timing, we take that we consider a source of bits where actually from the source 0 and 1 are coming with equal probability. I mean, this is not source, this is the property of the channel. But from the source from where we are collecting the bits, that source produces 0 and 1 with equal probability. So if we take n number of bits, then all are equally possible. 2 to the power n possible sequence are possible. Now the question is how many, by using the channel n times, how many mutually exclusive information we can send? This is the question. How many mutually information can be sent perfectly from Alice to Bob? This is the question. So you will be using the channel n times, and you know channel is corrupted. So never try to send 2 to the power n number of mutually exclusive information, because that will not work, because already you know channel is corrupted. So what you do? Rather, you choose among these 2 to the power n, you choose 2 to the power n into r number of points and try to send them through your n channels. Instead of taking 2 to the power n, you reduce the number by r. That means actually you are trying to, instead of trying to send n bits, you are trying to send n into r bits, where in r will be strictly less than 1. You try that and you see whether you can send them perfectly. And we will see what is the condition. Now, take one sequence of n bits. Let all are zeros. Because now all the zeros you are sending one by one through this channel. Then what are the possible sequence that will be generated in the output? Some student can answer. If all are zeros, let all are zeros, so n number of zeros, I am sending them one by one through this channel, and I am asking you, what are the possible number of sequences that will be generated on both sides?
Sir, if I may.
Yeah.
So if n is very large, then we must have some np number of ones and 1 minus p into n number of zeros.
Yeah, very good. Then what is the number of sequences?
Number of sequences would be just that 2 to the power n hp, as you told us.
Very good. Because from the start, I have told that only typical things we will consider. So you are correct. So from every point, that means every n bit sequences, because of this corrupted channel, both side there will be 2 to the power n into HP number of possible sequences. So from a point, here there will be 2 to the power n HP number of points. Now, let n use of the channel convey. So let n use of the channel convey r bits per channel, where r is strictly less than 1 because this is a corrupted channel. So we have chosen 2 to the power n number of sequences of 0, 1 generated from a source that produces 0 and 1 with equal probability. So now, from a 1 points, you are generating on the both side, 2 to the power n into HP number of points are generated. Here points means n bit sequence. So from a single point, 2 to the power n into HP number of points are generated. So from the 2 to the power n number of points, how many points will be generated? That is simply 2 to the power nr into 2 to the power n HP. Now, all these points cannot go beyond 2n because on this side there are number of total points which is equal to 2n. So if they have to be disjoint, all these things has to be disjoint, then it has to satisfy this condition. Because if this product is greater than 2 to the power n, then there will be intersection. I mean, this point is going here, this point is going here, and they are also disjoint. We are demanding that this is also disjoint so that Bob can discriminate. So to have this condition, this is a necessary condition, that 2 to the power n into r into 2 to the power n HP should be less than equal to 2 to the power n. This is a necessary condition. I think what do you want? We want that on both sides, each point generates a box which contains 2 to the power n HP points, but they are disjoint. And we want to maximize R so that this condition holds. So we want to find what is the highest value of R so that still this condition holds. So from here we will get R less than equal to 1 minus HP. And actually this is the actual capacity of the channel. You can tell it is CP, capacity of this channel. This capacity of this channel will be 1 minus HP because they are nothing to maximize, because already we have taken a source where bits are coming with equal probability. So everyone gets this point?
Yes, sir. So I have one question. I have one question here. So this is the fundamental limit, right? What you have shown.
Yeah.
The R cannot be.
Yeah. If this exceeds 2 to the power n, then some of the boxes will have intersection, and Bob will not be able to get the information.
Yes. So now, surely it shows that R for the beat kind of channel, R is less than 1. So which makes nr is less than n. So now my question is, in the encoding, which particular state should we take so that they go to different disjoint sets?
Yeah. So
Will
this
it
is
be very
again,
difficult?
yeah, very interesting question. And again, Shannon's discovery is so elegant. You can randomly choose 2 to the power n number of points from this 2 to the power n points. And all will work similarly.
This is very absurd, but yeah. Okay. Thank you, sir.
I have
Because of
Yes,
this
sir.
thing, you will get secrecy. You will see.
I see. Okay.
So this is Shannon Grace discovery that this 2 to the power n or out of 2 to the power n can be chosen randomly.
Okay.
This will give you power of, this will ensure secrecy, you will see.
I mean, I can assume that, okay, all are 0 and all are 1 surely will go to different disjoint sets because the NP number of flip would happens. But if I
Shannon,
choose any two
I
random
tell you,
points.
Shannon has proved it that you randomly choose 2 to the power nr and still it works.
Okay. This is very
And that will
interesting.
give you the power to the secrecy that you will see.
Sir,
Yeah.
I have a question just regarding this. I'm saying
Yeah.
that is it like it must be chosen randomly? Like if let's say I just choose the first sequence of NR, it will work or only random will work?
I think
any 2 to the power nr should work.
any 2 to the power nr will work.
But Guru, I am seeing
When
this problem.
n is very large, yeah.
I am seeing this problem in this way. You see, in 2 to the power n, you have 2 to the power n sequence. All are 0. N are 0.
Yes.
Last one is 1.
Yes.
And one of the 1 can be in n different place.
Yes.
2 of the 1 can be NC2 different places.
Yes.
These are my string. Now, problem is where? Problem is at channel level, no?
Yes, that is noisy.
So why a particular encoding should work? Because to it, everything is identical.
But Manika,
let me. I'm saying let's say n0 are there. If I say this n0 things, I know np number of 0 will come and 1 minus np number of 1 will, np number of 1 will come and 1 minus of np number of 0 will come. No, that is the channel's property.
Yes.
Let's say you take half of 0, half of 1. So isn't it these are IID similar kind of behavior I can guess, no? Due to this IID-ness, no? That any such things you should be able to choose, but once this is done, to the power nr you choose, that's all. That will completely completely block your this output space. Completely cover.
But Manika, the visualization is a little bit, I feel little problem in the visualization. For example, you consider that only first place is 1 and the rest of the n-1 bit are 0. Okay. This is one message in NR. And then take the second one. In the second place is 1 and the rest are 0. Third one is 1, rest are 0. In that way, I am taking.
Yes.
Now, in all those cases, what will happen? The number of 0 and number of 1 after processing through the channel, it would look like same for me.
But you try to. I'm saying you take 2 to the power nr kind of sequence, string. Another 2 to the power nr kind of sequence. Don't you think a deterministic stochastic matrix we can give from one to another?
Yes.
So before the channel action, that action is doing that things, no? Why that will be channel's property? That should not reflect, no? Why channel? Channel is the middle part. In these things, I am doing some deterministic processing. That should be done at the other things. Why? Otherwise, the channel will choose a particular input.
Manik, so I know that this is for n very large, but
Hey,
if we no,
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 we,
if we
all
go to
we are
the
talking
previous
about,
case,
all we are talking about A for n very large, no, Gurudev?
Yes, yes. Otherwise,
Yeah,
we'll come to
otherwise,
this point. If it is a small, then you have to be very careful to choose
yeah.
choose
Immediately
the
give you
to
counter
NR.
example.
Yeah.
because if we go to the 3 case where you were using the channel 3 times,
Yes,
and one time it may flip.
yes.
So there you have to actually choose your encoding very wisely.
Yeah,
Yes,
but for n large, very large, actually, this as Manik was telling, it will work like this. But still, we use the word this randomly chosen NR bits from this n bits, n bit sequence.
And sir, one more question. I think I'm rephrasing Mirda's question only. So where if I have a very big n string
Yeah,
and I have everywhere 0 except the first place. In the first place I have 1. And I take another string where only on the second place I have 1.
yeah.
So the typical sequences that I will generate from the first string and the ones that I will generate from the second string, won't they be actually same?
No, they will not be same, but they may have some intersection that you are asking.
Intersect. So yeah, they may have some this overlap, right?
Still, that's why Manik,
Yes.
maybe this randomness has a role to play.
Randomly chosen.
Yeah, what Ramu is actually trying to point out that, okay, I choose some random points because if I choose a random point, these kind of things, okay, first place is 1 and the second place is 1, that kind of things will not come in your encoding string.
Yeah.
Hmm.
That has to be assured, I think.
I see.
Okay, sir.
Okay, thank you, sir.
Achha. We are just generalizing this thing in the language of Shannon. So in the language of Shannon, so you are taking 2 to the power nr number of sequence or points, and for a given x, here that the number of string that will be generated is nothing but 2 to the power n into h y given x. For every x, it will be, for every x means for every points, for every x means for a single point, sorry, for a single point x, it will generate this number of points, 2 to the power n into h y given x. So again, for securely sending your information, this condition, here I have taken general thing, 2 to the power, on Bob's side it is 2 to the power n h y. So this condition has to be satisfied. So r is less than equal to this quantity hy minus hy given x, and already you know in nothing but mutual information. Then the mutual information has to be maximized over this px, where px is px is the probability where these bits are coming from a source. 0 and 1 are coming with some probabilities p and 1 minus p, and you have to maximize over that. So this is the definition. This is the thing that we call is channel capacity. So what you do, you have to maximize this mutual information, but only variable that you have control over, that your source from where these 2 to the power n or number of points will be generated, and you have to maximize over those probabilities from the source. Now, I am trying to understanding this thing in a with few bits. So I take this kind of channel that Alice's bits may be 0, 0, 0, 1, 1, 0, 1, 1. All are coming with equal probability. 1, 4, 1, 4, 1, 4, 1, 4. Now, after these two bits sent by these two channel, what Bob receives 0, 0, 0, 1, 1, 0, 1, 1. That means between Alice and Bob, channel is perfect. Channel is behaving perfect. But Eve is also receiving something. For 0, 0, Eve is receiving 0, 0, but with probability half, and 0, 1 with probability half. So total probability, as these are probability 1, 4, 1, 4, 1, 4, 1, 4. So Eve will receive 0, 0 with probability 1, 8. Eve will receive bits 0, 1 with probability 1, 8 in this way for all the cases. So what happens with Eve? You see, Eve's bits, second bits may be flipped. So this is a very particular kind of channel that for Eve, only second bit may be corrupted. First bit remains same. This is very idealist kind of thing, but to understand things, I have to consider such cases. And I will talk what is my problem later. Why I cannot avoid, because it is very bad. Now I am fixing for the Eve that second bits may be corrupted or may not be corrupted with equal probability. So gets my point? So Alice sending 0, 0, Bob is getting the correct bits 0, 0, but Eve second bit may be flipped with probability half. So if for 0, 0, Eve will receive either 0, 0 or 0, 1 with equal probability. When Alice sends 0, 1, Bob again will receive the correct, but Eve will receive 0, 1 or 0, 0 again with equal probability in this way for all these four possibilities. So you can express these probabilities in this way. Between AB, P of ij for Alice and ij for Bob is equal to 1/4. So it is perfect channel for between Alice and Bob. For Alice and Eve, ij is equal to ij is equal to P. Oh, sorry. This is AE. I am wrong. This is not AB. This is AE. So ij means for Eve, bits remains correct is equal to PAE ij plus 1. That means second one is corrupted or flipped, and that probability is also 1/8. And if you calculate ij for A, ij for B, and ij probability of ij for A, ij for B, and ij for E, all are 1/4. Okay, is there any question? I have taken a very, very simplified channel where two bits are reaching Bob perfectly, but when it is reaching Eve, second bits may be flipped with probability half. So calculate IAV between, that means mutual information between AB. It is perfect, so it is true. Because two bits are going perfectly to Bob. But if you calculate IAE, mutual information between Alice and D, it is 2 plus 2 minus 3. You look at these probabilities. So it is 1. But you can trivially tell it that you will see this first bit. And that is going correctly. So you will get the 1 bit correctly. So that's why mutual information between Alice and D is equal to 1. Now let us see how secrecy can be derived from here. So Alice encodes 0, not to 0, 0, neither to 1, 1, but equal mixture of them. Alice encodes 0 with equal mixture of 0, 0 and 1, 1. That means when he wants to send 0, he randomly chooses either 0, 0 or 1, 1. And when he wants to send 1, he randomly chooses either 0, 1 or 1, 0 with equal probability. And send these 2 bits through that channel that I defined here. This channel. This is the channel property. Now, Bob receives correctly. If Alice sends 0, 0 and 1, 1 randomly, he will also get 0, 0 and 1, 1 randomly. And if he wants to send 1, that means he sends 0, 1 or 1, 0, equal mixture of 0, 1, 1, 0. Bob will also receive equal mixture of 0, 1 and 1, 0. So Bob can get either, or Bob can understand whether it is 0 or 1. But Eve has a problem. If Alice wants to send 0, Eve will get all these strings with equal probability.
I think, sir, there is a typo in your
Where?
Eve part. In the Eve part.
Where
Eve part, all are not there. 1, 1, 1, 0, 1, 1, 1.
That's it. See, sometimes I copy and I copy the wrong thing. So first one, 1, 1, 1, 0, 0, 1, 0, 0. So all are wrong. There will be all 4 actually. All 4 will come, see? 0, 1, 0, 0, 1, 1, 1, 0. Here it is correct. But here it is wrong. So actually, my mid is correct. All these 4 will come with equal probability. And for 2 bits, these 4 are only possibility. And for 0, Eve will get all these 4 with equal probability. For 1 also, Eve will get all these 4 with equal probability. So Eve will not get any information about this bit. So this bit will be shared only between Alice and Bob, and this is secret bit. And if you calculate, so secret bit is one bit of secrecy they are deriving from such channel, and you see this is equal to mutual information between AB minus mutual information between AE. So 1 bit of secrecy can be obtained. So I'm trying to tell that rate of secrecy is given by mutual information between AB minus mutual information between A and B. But this is not a very good example, I cannot create, but I have tried little bit improved another example where here actually to Eve nothing is conveyed. Here to Eve nothing is conveyed because it is completely random. So I'm trying to make Alice and Eve also get some information. So I will use thrice, 3 times, 3 bits channel. I mean, 3 1-bit channel. So Alice chooses all these possible 3 bits. So there are 8 possibilities, and again with equal probability. Now, property of the channel, again, these are idealist, very idealist. For Bob, only last bit may be corrupted with probability half. So 0, 0, 0 will go to either 0, 0, 0 or 0, 0, 1. Both are with equal probability. So last bit of Alice, when it reaches to Bob, may be or may not be corrupted. So these are the possibilities for Bob, again with equal probability. For Eve, any 1 bit will be corrupted. If Alice sends 0, 0, 0, either there will be no corruption or one of the bit will be corrupted, but it may be corrupted in any one of the place. So for Eve, these are the possibility. For 0, 0, these are the possibility. For 1, 0, 0, these are the possibility. Still, I may be wrong somewhere. So later you check.
Okay, sir. Okay.
Now, again, in terms of probability, PAB IJK is equal to PAB IJK, last one may be flipped. So it is 1/16 because this is all this probability 1/8 and their probabilities are up. So all this Bob's thing will be 1/16. And for if, as promised, from a single points, then it may generate 4 points again with equal probability. So maybe there may not be any corruption. There may be corruption on the first one. There may be corruption on the second one. There may be corruption on the third one. All are equally probable and probability is 1/32. But again, for if it is good that there may be corruption of the one channel, but which one we don't know. But for Bob, again, it is idealized. Only last bit may be corrupted. So I will tell you that whether, because I want thing so that this number is 2, you can express them as power of 2. But I cannot create a channel for Bob and Deep so that corruption may happen anywhere. And still these numbers are very good, like 116, 132 or 164. I could not do it. So I will ask you, if I increase one more bit on IHS side, whether this corruption may occur in randomly in one of the channel or 2 of the channel, whether in this way, this kind of number can be brought. I failed. But anyway, for this channel, if you calculate IAB, I mean, mutual information between Alice and Bob, it is 2. Mutual information between Alice and Deep is equal to 1. So, again, see, you can derive one bit of secrecy because IAB minus IAE is equal to 1. That I will prove later. But now I am claiming that difference between these 2 mutual information give you secrecy. So, how will you secrecy? Now, as Mir's point will come, whether we will choose this thing completely random. Now you will see that at least for this finite number, 3 numbers, you cannot choose them random to generate secrecy. Manik, you closely look at this thing. See, here, let Alice wants to generate 1 bit of secrecy. What Alice do, for 0, he will send 30 or 31 with equal probability. Okay? And when it reaches to Bob, this 30 may be 30 and 001, but for Bob, and 111 for Bob will be 111, I mean it will not change, or 110, that means third one will change. Similarly, Alice encodes 1 to this 100011. You see, we have chosen this thing in such a way that these 2 bits differs in all the position. These bits differ in all the position. So these 2 bits also differs in all the position, you see. And this will also for Bob, it will generate. For the 100, it will generate 100101. And 011, it will generate 011010. Now these 2 are again disjoint. So Bob will get 1 bit of information. But for Eve, all these will come. If I am not wrong. Mir, have all these bits have come?
I think so. I think so.
So as they will come with equal probability, so Eve will not get any information about this bit. So it will again remain secret.
Sir,
Yes.
so you were asking, no, in the previous slide, can we come up with a better example?
Oh, it is not better. It is better for Eve. But you see, I cannot do it. For Eve, I have taken the channel such that it may be corrupted in one place, but randomly, any one of them.
Yes. So means what I was saying is, so Bob, it is little bit special kind of channel, idealistic channel, right?
I will ask you to do the same thing for Bob. Still, you derive the number so that it is comes in the power of 2.
Means I was saying can we not do like that? Let's say for Bob, you make the channel that it will be corrupted in any of the one position.
Yes.
But for Eve, it will be corrupted in any of the two position.
Then what will happen? Possibly this IAE will be 0. I want to make it non-zero.
Means IAE will be 0. That you want to make non-zero. I see.
Yeah.
But in that case, IAE would not be non-zero. I think it would be. Sorry, it would be non-zero.
It will be non-zero. No?
It will be non-zero
it
because
would be
some
non-zero.
information is still going.
But it will be that bad number, I think.
Yeah. That would be very bad number with some fractions. With some fractions, it would come, and it would not be this kind of nice example.
Okay.
So
Okay.
I will ask you. Actually, I tried. With 3 bits, you cannot do it. Maybe 4, 5 bits you may try, but still for 4, 5, we are thinking that this some numbers is coming which is not in the power of 2.
I see.
But you can try.
Okay.
But if number is very big, then slide cannot be prepared. That is another problem.
Yeah. Okay.
At least slide cannot be prepared in this fashion. Maybe in this fashion you can do it. But here there is another possibility. You can encode 0 in this way and 1 in this way. But if you look at this thing, look at the 8 possibilities, there is another protocol. You encode 0 in these 3 bits and 1 in this 3 bits. Here also you see every position they are different. And again, possibility for Bob is this 4 for 0, possibility for Bob this 4 for 1, and again they are disjoint. And for Bob, it is equal, same. So instead of taking these encoding to send secrecy, you can also take these encoding for generating secrecy between Alice and Bob.
Guruda,
Yeah.
So the way that I understood is the protocol from Alice to Bob is that so you have 000, a 3-bit string, and you know that only the third use of the channel is corrupted.
Yeah.
So we know that with half probability it will be 000, and with half probability it will be 001.
Yeah.
Right? But suppose we don't know that in which use the channel is corrupted, but we know that okay, at most one use of the channel is corrupted.
I am telling I failed to do that. No, I failed to do that, but I have in mind that this number I want in the power of 2.
Yeah, but
so,
what I am saying is that so in that
so
sense,
you may try, but I was not successful.
So what would be Bob's possible bits? It would be 000, 001, 010, and 100, right?
Yeah.
Like in each time, at most one of the bit flips, or no bit flips. So that should also be 1/4, right? With 1/4 probability, Bob will get either 000, or when the third use of the channel is corrupted, you will get 001. When the second use of the channel is corrupted, you will get 010. When the first use of the channel is corrupt, you will get 1.
Now, what we are trying to tell?
So with this way, there should be some power of 2, right? Always, if we have.
I am trying to tell that I have taken very special kind of channel which is acting Alice and Bob in a particular way, but between Alice and Eve, it is little bit better that corruption may occur randomly in one of the channel, but for between Alice and Bob, it is very special. But till now I am successful with such kind of channel because there is another constraint that I want these numbers in the power of 2. So that IAB and IAB become full natural number.
Okay. It's only for that reason you want power.
So that's why I'm asking you people to have maybe more than 3 bits and have random kind of channel between Alice Eve, Bob and Alice Eve, and try to get this thing, but I fail to do that. Some with 4 things, this number is coming 1 by 56. Now 1 by 56 cannot be expressed as something 2 to the power something. So that is a big problem. Then I cannot use this simple argument without using large N.
Okay.
Yeah, so there is 2 secrecy protocol. One secrecy is you are encoding 0 in this fashion and 1 in this fashion, and you get 1 bit of secrecy. But there is another possibility. You encode 0 in this fashion, 1 in this fashion, still you get 1 bit of secrecy. But remember that in both the cases, when you encode 0, in all these 3 places, the possible bits are different. It is 0, 0, 0, so 1, 1, 1. 1, 0, 0, in all the 3 places, they are different. Similarly, here also, 0, 1, 0, 1, 0, 1. 0, 0, 1, 1, 1, 0. All the 3 places, they are different. But with this encoding, also you can send you can generate 1 bit of secrecy between Alice and Bob, and you will have nothing. Now, interestingly, you can use actually 2 to the power 3 bits. So we are considering 2 to 3 bits. So there are 8 possibilities. No. So if any possibility, if any of the possibility comes to Alice, Alice can generate secret bit with Bob. See how. So what Alice do, and this is also public. Alice takes the full 8 bits. So these contain all the 8 sequence of 3 bits. Now he subdivide these 8 bits in 2 groups. Name the first group as L is equal to 1. Name the second group as L is equal to 2. LO is equal to 1, and all of them contains 4 3-bit sequence. This is L is equal to 1, LO is equal to 1 contains 30, 31, 100, 001, and L is equal to 2 contains 010, 101, 001, and 110. So these 2 groups. Now, again, you subdivide L between M. So there are 4. Now we have taken in a group which is named as M is equal to 1. So it is 000, 111 for M is equal to 1, and M is equal to 2. It is 100 and 001. And you also name them. This is S is equal to 1. This is S is equal to 2. Similarly, here S is equal to 1 is equal to actually value of S is equal to 1, it is 100. Value of S equal to 2, it is 001. And similarly for L2 also you do the same thing. Now what you do, so let any one of these 8 has come to you, and you want to generate 1 bit of secrecy with Bob. What you do? You send the information of L.
Here, L and S you have done in a particular fashion.
একটু জোরে বলো মানিক।
L, M, and S is subdivision. Have you done in a particular way something keeping in mind?
In a particular way. Actually, there are 2 possibilities. The secrecy protocol you see, there are 2 possibilities of encoding.
Yes.
So I am taking it that randomly one of these 8 possibilities has come to you, and you want to generate 1 bit of secrecy. How can you do it?
Nice.
So let you have received.
Sir,
01.
I think there all the 8 strings are not there, right? For M equal to 2, it will be 100 and 011, right? There is a typo, I think.
Because all 3 positions will be different. So here it will be 1, no?
Yes, sir. Yes, sir. Here it will be 0, 1, 1.
0, 1, 1. Yeah. But you understand what I want to do.
Yes, sir. Yes.
So let randomly one bit as 1, 3, the 0, 1, 0 has come. Let this 0, 1, 0 has come to Alice. Then what Alice do? Alice, by using a bit of information, tell whether L is equal to 1 or L is equal to 2. To Bob. What is public, and it can also listen to, it can also learn whether it is L is equal to 1 or L is equal to 2. Okay? Now, after knowing L1, it becomes like this. Things becomes like this. And if L is equal to 2, things becomes like this. So for a random 3 bits, Alice has to inform Bob whether it belongs to L is equal to 1 or L is equal to 2. If L is equal to 1, this thing works. If L is equal to 2, this thing works. So this information of L has to be sent to Bob. But if we will not get anything, because to learn these bits, Eve needs to know M is equal to 1 or M is equal to 2. But that is not announced, and that is the secrecy. So here M is the secrecy.
If kichu
And actually M is equally probable in all the L's. That's why he is not getting any information about the M.
Yeah. So only information of L has to be communicated to Bob, which also Eve can listen to, but that does not help it. To learn the actual information, Eve needs to know whether M is equal to 1 or M is equal to 2. But you are not announcing M because, and not only that, M is the secrecy. So 1 bit of secrecy will be derived if L is announced. Get my point?
Sir, may I ask a question? I think I missed something. So
Yes.
Alice is only communicating this, Alice is only broadcasting the result of L.
Yeah.
But they're not communicating any other bits, is it?
Yeah. So let L is equal to 1, then things becomes like this.
Yes.
And if L is equal to 2, things becomes like this.
Yes.
So in both the cases, 1 bit of secrecy can be created between Alice and Bob. Here, the novelty is that out of these 8, anyone is coming to Alice, and Alice can generate secrecy with Bob. So Alice has to give the info after having these 3 bits. Alice has to tell whether it belongs to L is equal to 1 or L is equal to 2. If L is equal to 1, this thing works. If L is equal to 2, this thing works. And in both the cases, 1 bit of secrecy can be generated between Alice and Bob. I am telling all these things because I will go to the general case and you will easily understand how the general case works.
Probably, sir.
Ah.
Probably what Punika is asking, that this L is extra information apart from these 3 bits. Alice has to declare.
Yes.
Declare L separately.
No, see, I am telling that say some random bits has come. Let 110 has come to Alice, and Alice wants to generate secrecy. Now 110, he will see in which group it is. 110.
L equal to 2.
L is equal to 2. So he will send the information that L is equal to 2. It belongs to L is equal to 2. After that, this thing works.
No, sir, what I wanted to ask is Alice will send 110 as well as L equal to 2.
Yeah.
Is that so?
110 he will send through the channel. And publicly he will announce L is equal to 1 or L is equal to 2.
Oh, okay. Now I understand.
This
Thank
public
you.
announcement. That's why I'm telling it can also listen to that.
Yeah. Okay, sir.
So by spending 1 bit, he publicly announces whether L is equal to 1 or L is equal to 2. After that, secrecy will work. For L is equal to 1, secrecy will work in this way. And if L is equal to 2, secrecy will work in this way. And all these things are previously announced between not only Alice, Bob, and Deep, but the whole world. But of course, you have considered very particular kind of channel. Very particular kind of channel.
Sir,
So,
maybe it would be repetitive, but I'll ask you once again, just because. So, I mean, if I just stick into one of the protocol, I mean, for example, right now in your slide, it is given that, okay, if 0 is there, so 0, 0, 0, 1, 1, 1. Now, if we find out the mutual informations, right now, if we find out the mutual information between the left side 0 and whatever Alice Eve is getting, that is 0. Because for the 0, Eve can get all the sequences. So the mutual information between this message n is equal to 0 and the Eve part is 0. Whereas in the same for the other.
But don't calculate from here. You have to calculate from here.
No, that is okay, sir. But I'm saying in case of a secrecy, our
in case of the secrecy, you are correct. So when I restricting this thing to 4 bits, then mutual information belongs between Alice and Bob also reduces. It becomes 1.
Exactly.
And Alice and Deep, it becomes 0. Yeah,
exactly. So that is the main purpose of the secret thing, that okay, nothing, Bob Eve will not get anything. So that is the main purpose. So now for this secrecy protocol, I'm happy with this secrecy protocol because this is working. Bob is actually getting 1 bit of information because he is getting 2 different patch. So in this kind of encoding decoding, actually it is happening. Now I think what you are saying that okay, if some other input comes, for example, if the input comes like 1,
if the input comes randomly, these
exactly.
encoding they are fixed. These encoding they are fixed. So this is the so bits are coming randomly. Still he can use it. Only thing he has to announce, because Bob will not know it. That's why he has to announce whether it belongs to L is equal to 1 or it belongs to L is equal to 2.
So that is the novelty of this protocol. I mean, what you are saying right now.
Because
earlier it was very clear.
My motivation is going to general case, so I am trying to motivate towards that direction.
Exactly. Okay. Thank you, sir.
Now, how to derive secrecy in general? Now you are using general channel, like P with P, it will play and 1 minus P, it will not play like this. And secrecy can be derived between Alice and Bob if the following condition holds. That means mutual information between Alice and Bob is strictly greater than mutual information between Alice and Eve. And the rate will be this quantity per use of the channel. So, from now on, as I told you, we will only consider typical sequences. Now, from a source, X is coming with probability Px. So, what are the possible number of sequences with Alice? 2 to the power n hx. Okay. Now, already we have learned among these 2 to the power n hx, 2 to the power n, so I am considering some channel between x and y, and for this is not h. Actually, I have sometimes confused this thing. Actually, sometimes I use h to understand mutual information. Sometimes I use I to understand mutual information. But from this symbol x, xy, you will know that actually I have meant for mutual information. So this is actually, this hxy is actually mutual information. Now, so x colon y, from this symbol x colon y, whether I use h or I, you will understand this is mutual information. But already we know that among these 2 to the power nh possibilities, the if it is restricted to 2 to the power n into a mutual information between x and y, that number of mutually exclusive information you can send reliably to Bob. Okay, get my point? And so how many such groups you can create among the 2 to the power nhx? So total number is 2 to the power nhx. And you can send by using n number, channel n times, you can send not 2 to the power nhx mutually exclusive information. You can send only 2 to the power n into h x colon y number of mutually exclusive information. So if you group, so how many such groups containing this amount of this amount of sequences are there among 2 to the power 2 nhx? You have to divide it, and I give this number L, where L is I number. So I put this box. Every box contains 2 to the power n into hxy number of points, where each point is nothing but sequences of x's. I mean sequence of 0 1s. So each box contains this number of points, and how many boxes are there? L. Because by dividing 2 to the power nhx by this amount, you get this number, and you name each box as L is here. It is L is equal to 1. It is L is equal to 2. It is L is equal to 3, and finally L is equal to capital L. If Alice sends a point and tells the value of L by using, so how many bits will be required to send the information about L? You have to spend nh x given y number of bits to convey the information of L, whether L is equal to 1 or L is equal to 2 or L is equal to 3, something like that. If Alice sends a point and tells the value, so Alice gets a point randomly and see in which L it belongs to. So Alice gets a point of n bits, and Alice first check in which L it belongs to, and send that information of L to Bob by using 2 to the power n h x given y bits of information, so that Bob can identify the point and hence gets these bits of information. So gets my point? Because this number of mutually exclusive information Bob can reliably distinguish. If information of L is given, so L's are called cold code for reliable information transmission. That means if Bob knows the box, if Bob knows the number of box, then he can distinguish among all these points in a particular box, in every box actually. So if he knows the number of box. So after having a random bits of sequences, Alice convey the information that the sequence belongs to which box. And then Bob can reliably know the bit string. Similarly, similar thing is with also if. It is again.
Guruda. Guruda, this is Nirman from Hyderabad.
Yes.
So actually what I was trying to think is that as you are saying that Bob gets 2 to the power n I x y bits of information.
No.
This last point that you have written, hence he gets 2 to the power n I x y bits of information.
Here.
The last line before the red line.
Bob can identify the points and hence gets, oh no, sorry, again wrong. N into h x colon y bits of information. Yeah, you are correct.
So that
or gets this amount of mutually exclusive information.
Yes. So
again, I am wrong. Yeah.
That thing in the power is actually the mutual information between x and y.
Yeah. Of course.
So that means if I say that mutual information is a kind of correlation between X and Y, more correlation, more the bits of information?
Yeah. If perfect correlation, then it is N.
Then it is N. Yes. Okay.
So what I am trying to tell in this slide, that if the information about L is given, number for L is given to Bob, Bob will reliably distinguish among the points. Similarly, for if, again, if is given this number S, sorry, if is given this number S, because similar thing, I have taken mutual information between Alice and Eve, and again, if is given this number S, where S is equal to 1, S is equal to 2, S is equal to 3, and each coin, each box contains this number of points, then if Alice sends a point and tells the value of S by using these amounts of information, it can also identify the points and hence gets, again I am wrong, N into H, X colon Z bits of information. These sets are called privacy amplification set for some reason. That I am going to make it clear. Why I called it privacy amplification set. But it is true that if the information of S is given to Eve, then Eve can also identify the points. Let Alice gets the points randomly, and if it tells in which S it belongs to, and if that information about S is given to Eve, Eve can also get the bit string. Now, let us see how many privacy, I call it privacy amplification set. These sets I am calling, which contains N into 2 to the power N into H X colon Z, number of points. Actually, each box contains this number of points. I call them privacy amplification set. Why? It will be clear in the next slide. Now, how many privacy amplification sets are there in a set identified by L? Now, come to this point. Which one is greater? This, sometimes I use H, sometimes I use H, but to mean the same thing. So IXY is greater than IXZ, is strictly greater than IZ. So which box will have more size? This or this? Some students, can you tell me which box will be larger? That means which box will contain more points?
Sir, this
First.
yeah, first one.
First one will contain more points. So sometimes it may happen that actually these are big boxes, and actually it may contain some small boxes, which is called privacy amplification set. And that's the thing I have done. So how many privacy amplification sets are there in a set identified by any L? That means L is equal to 1, L is equal to 2, L is equal to 3, up to L is equal to capital L. The number is the following. So each, for a given L, there are this number of points, and for a given S, it has this number of points. So after division, you get this number, which is equal to M. This is nothing but 2 into 2 to the power N into difference between mutual information. Sometimes I use H and sometimes use I. Again, I have made the confusion. So 2 to the power N into mutual difference between the mutual information between Alice Bob and Alice C. And this number is M. M is again, M can be, M is equal to 1, M is equal to 2, M is equal to 3, up to M is equal to capital N. So what you do, so for a given L, actually I should have written here, for a given L, you can subdivide L between various M, where each M is nothing but a privacy amplification set. And every M actually, so M is equal to 3. How many points it contains? It contains 2 to the power n into h x colon z. If the number M is given to if, then it can learn exactly the points. But you will see in the protocol, L will be announced, not M. M will be used for secrecy. That's why if cannot get any info. For if, all these things are equal. Like earlier case, these two sets are equal for if. Or this set, this set, this set, this set, all are equal to if. Here also, all these M's are equal to if. Because all the boxes will generate all the possible sequence of n bits on if side. So now come to the protocol. Alice receives one n-bit string x, say it is x. Out of this 2 to the power n hx possible string from the source. So one bit string of n bits comes to Alice. What Alice first checks, and Alice sends them to Bob by using a channel n times. Bob and Eve receives y and z respectively. Now, after this thing, Alice sent the information of L. That means L, he will check the X that is coming to it contains to which L. That information will be sent to Bob. But it is public announcement, it can also listen to it. Bob immediately can identify the string X as well as the privacy amplification set S in the Lth set, which contains X and hence can get the number N. Because if actually can, for a given L, if actually can distinguish among all the possible points in this big square. But if can also know whether it belongs to M is equal to 1, whether it belongs to M is equal to 2, whether it belongs to M is equal to 3, we will note that.
And in this picture, the earlier picture, can you go? In this picture, where is S?
Oh, SAR actually, SAR is the number of points in M.
I see.
So first here S is equal to 1, S is equal to 2, S is equal to 3.
Understood.
So now Alice sent the information of L. Bob immediately can identify the string, but as well as the privacy amplification set S in the L set, which contains X, and hence can get the number N. For Eve, knowing L does not help. To learn X, he needs to know S. I am again wrong. He needs to know M. Again, I am wrong. If he knows M, then he can identify among these points. He needs to, again, I am wrong. To learn X, he needs to know M. Otherwise, all M are equally possible for him. All the M are equally possible for him. Hence, M is the number that it cannot know, and hence this number is the secret key between Alice and Bob. And what is the size of M? Size of M is this thing. So how many secrecy will be generated? N into difference between mutual information between Alice Bob and Alice. This amount of secrecy will be generated. To encode M in bits, we need this number of bits, and hence a number of bits of secrecy will be generated. So per channel, you are generating this amount of secrecy. Difference between mutual information between Alice Bob and Alice. Now come to the full picture. So this is the full 2 to the power nhx. Now Alice gets a string randomly. he will check whether it belongs to L is equal to 1 or L is equal to 2. Every L is again subdivided between M. M is equal to 1, M is equal to 2, M is equal to 3, M is equal to 4. Similarly, for given L2, M is equal to 1, M is equal to 2. And S are the string itself. So choose a M, let in this L, this is the M is equal to 1. In M, this is S, first one is S is equal to 1, second one is S equal to 2, third one is S equal to 3. Similarly for all of them. Now the picture is, after passing through the channel, this thing for Alice, for Bob, all these points in this given L is equal to 2 or L is equal to 3, for any given L, all the points will be mapped into disjoint sets. So he can identify any points. But they have subdivided every L in terms of M. And so all these M's, so after knowing the bit string, Bob will know in which M it belongs to. Because L has already been announced, let L is equal to 2 has been announced. So he will look into this thing and see his points belongs to M is equal to 1, or M is equal to 2, or M is equal to 3, or M is equal to 4. And that number will be the secret string. Because if for a given M, all M are equally valid for if. Because if you take these M and consider all the points, then all these points cover the whole set of if, which is of size 2 to the power xj, hj. So if will know knowledge about M, and that is the secrecy. Yeah.
So each of the L in the above picture, blue region, left hand side blue region covers the Y of the Bob space that you are saying.
Yeah. All the, if you take the collection of all L, it is full 2 to the power n hx. So I have divided 2 to the power n hx in L boxes. Then inside the L boxes, I have subdivided them in M boxes, where M is privacy amplification set. And inside M, there are points that for M is equal to 1, M is equal to 2, M is equal to 3, they are actually equal for E. Because all of them covers the full region of E. So see, L is announced and M is the secrecy. You cannot increase the secrecy because you are going to announce L is equal to 1 or L is equal to 2 because some bits are some n bits are coming randomly. So first you have to check whether it belongs to L is equal to 1, L is equal to 2. And if you don't give information of L to Bob, then Bob cannot distinguish among these points. Because Bob can distinguish not 2 to the power nhx number of string, but 2 to the power n into I x colon y number of string. Get my point?
Will you discuss something more also today, or you?
No, I am coming to the end. So conclusions. So again, I have confused. Either I should write H in all the places or I in all these places, but I have confused. So mutual information between Alice and Bob is strictly, if mutual information between Alice and Bob is strictly greater than between Alice and Eve, then it guarantees secrecy. But still, these are the mathematical results. Because classical laws cannot guarantee the generation of such population which satisfy this condition. I mean, physical laws cannot, physical laws in classical world cannot guarantee this condition. Now, quantum mechanics restricts distinguishability of different states. So this is one property of quantum mechanics, that you cannot clone or distinguish among different quantum states if they are not orthogonal. And there is another property, entanglement is there, that has some monogamous nature. All these guarantee, we'll see in our next lecture, all these guarantee the generation of secrecy by using quantum laws, and which classical laws could not guarantee. This will be the essence of our next two talks. Yeah, I have finished.
If you have any question, you can ask.
Gurudev, I had one question. This is Nirman. So you said that if the mutual information between X and Y is strictly greater than the mutual information between X and Z, then that will guarantee secrecy.
Yeah.
Okay, but in the second statement, you are saying that classical laws cannot guarantee the generation of such correlations. Can you please tell us why are you saying such a?
Because everything is copyable, everything is knowable. So there is no laws. I am telling, by some technique you can do it, but
Okay.
but no laws support it. That what information will be shared between Alice and Bob cannot be shared between Alice and Deep. This cannot be guaranteed by laws. I am telling.
So, Gurudev, the same thing. Can you go to the this first slide where the binary channel you have discussed? Next one. So you see, Nirmanda.
Manik, yes.
Yeah. You see, look into this Gurudev's example. So Alice is sending 0, 0. What Bob is receiving? 0, 0. Perfect. Alice is sending 0, 1. What is Bob is receiving? 0, 1.
Yes.
1, 0, 1, 1. 1, 1, 1, 1. So Alice to Bob, it is perfect channel. And Gurudev shows that, okay, some information is going to you. Okay. Let's say I say this one. Let's say Alice is a qubit. The qubit is perfectly go to Bob. What environment, what it will get? If it is a qubit, the arbitrary qubit perfectly goes from Alice to Bob.
Okay.
So any information of qubit can Eve get. Because otherwise then no, because then cloning will be violated, no?
Okay. Okay, so that means you.
Now I'm saying quantum mechanics, you have a rule. Oh, cloning I have to, no cloning I have to satisfy. That means if you have a perfect identity channel from Alice to Bob that transfer a qubit information, you know law is nature is saying that no information can go to the environment. But classically, how will you guarantee that? There is no guarantee. What Gurudev is saying, you can copy. Actually, it can copy these things and that things can go to them. If copy this information and give the same thing to Bob. But that is not possible in quantum. You understand, no?
So that means you are saying that the quantum laws that we are having is actually ensuring that there is a non-zero difference over there.
There is a physical way to do that.
Yeah, Manik's example, extreme example is very good. So that's why in quantum teleportation, you can send the quantum information only to one party.
Yes.
Now
So it is the extreme case. It is the extreme case. But to understand it, it is a very good example.
Yeah, we have to now go to noisy scenario or all.
Yeah.
And this is nothing but what I am saying in a variant of entanglement monogamy kind of.
Yeah.
I'm saying, should we say that no cloning is the things which which is assuring these things, or no broadcasting is the main thing which is assuring this?
Yeah. So we are not particularly telling something, but in general, these quantum mechanical laws will help you. Main thing are something like this. Maybe you can write is quantum analysis, distinguishability, or no broadcasting, or no cloning. All these things you can write, but I have written just these two.
Okay, okay.
Actually, whole quantum laws are important.
Yeah. Sure, you can ask
Hello.
your
Yeah, yes, sir. Yeah, I have a question. Like the protocol that you have like just told, it distills 1 bit of privacy, right?
This one.
Uh,
Yeah. Or
yeah.
which one you want? This one or this one?
The last one that you have discussed is for general case. Yeah.
Let me come. This one. Oh, no.
For general case. General case.
Oh, for general case. Which one I report? Yeah.
Oh, yeah. So it distills 1 pbit, right? Of secrecy. It distills 1 pbit of this secrecy.
No,
one private
Here,
bit.
here
Oh.
I am distilling each different per channel. I am deriving difference, the amount which is equal to difference between the mutual information between Alice and Deep and Alice and Bob.
Okay, that much. Okay, that much bit is distilling. Yeah. Okay. I was confused.
In this example, I have created in such a way that 1 bit of secrecy is derived.
Yeah. Okay, thanks.
But it is to motivate you for the general result. All these LMS come. This here is only L is equal to 1 and 2, M is equal to 1 and 2, and also S is equal to 1 and 2. So this is very trivial kind of cases. But to motivate you for the general result, I name them in this way. Otherwise, these things are very trivial. But I think I could motivate you to understand this most general case.
Yeah. Sure.
And I don't find any book where these things are discussed. There is a paper by Conard in 1973 and some other people in 1992. I read their paper, but they are information theorists, that's why they don't care also. But they have written their paper in such a way it is very difficult for us who are in physics to get their thing.
So historically, privacy amplification, the Shannon start or later people?
No, later, 1973, it was discovered money. Somehow I am thinking why Shannon actually easily could discover it. But somehow in 1950s, this question of secrecy either was not important or these information theory people, they were not interested. Otherwise, by just one more line, Shannon could tell this difference is nothing but secrecy.
So who discovered that first?
Conard, possibly name is Conard in 1973.
I see.
But better paper were written in 1992 by some other people.
Understood. So if there is no more question, we'll meet next Thursday, no?
Yeah, next Thursday, 8th of May. The same time, around 4 o'clock.
4 o'clock. So same, you will send the link.
We'll send the link. It would be the same link, but I'll obviously give you another reminder. Okay. Thank you all. Then I'm stopped recording.
Thank you so much. It was a fantastic Guruda. Thank you so much.
Thank you.
To meet